It is time to begin Unit 5, which is dealing with the idea of exponents. So when it comes to exponents, when we think about our order of operations, we say ask for several extra. Extra is the exponent aspect when it comes to doing math in the correct order. So when we start looking, so let's get into Unit 5, Lesson 1, taking notes on page 261. And we always want to start once again with our objective for the lesson. What is our objective for the lesson? Well, let's read it and then we'll do some explaining. Okay? It says, I can do what? I can write a product of whole numbers, fractions, or decimals as a power and write a power as a product of factors. Now, for some of you, that might be like Charlie Brown's teacher talking to you. Wah, 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 wah. You're not really sure what's being said. So let's break it down and look at it. If I go back into my math packet that I gave you earlier this year, we look at the words into math page, which is where all the symbols are and specific words that are used in mathematics. Then I can look and find the word product. And if you don't already know, product means the answer to a multiplication problem. So we're going to be doing multiplication when we're talking about exponents. It's not going to be adding, subtracting, it's not going to be dividing, it's going to be multiplication. But what am I multiplying? So when I look at the idea of a power, write this down so you know what your definitions are. But a power is any number with an exponent. So I have a base, I have an exponent. I want to know what those means. But the meaning is that we have a math expression. So just a quick review, if you don't remember the difference between expressions and equations, the word equations starts with the root word of equa, which is the same as our word equal. So I know when I have an equation, I'm going to have an equal sign and an answer. Expressions are math problems without an answer. So it's a math problem that I need to solve, such as this, 3 with an exponent of 4. So when we have what is called a power, then this is a math expression, and I say this as 3 to the 4th power. So I know that I have some multiplication going on in there, but I have to figure out what that means. Well, what that means is I'm going to take 3 and I'm going to multiply it by itself 4 different times. So my math expression becomes 3 times 3 times 3 times 3. Once again, I take my base, the 3, and I'm going to multiply it by itself however many times the exponent tells me. If there was a 10 there for the exponent, I would have 10 different 3's written down and I would multiply them all together. So when I do that math, then I have to be specific about what is my base. My base is my large number, right? It's any number that has an exponent or has a power written with it, used as a factor. Well, what is a factor? Wow, we're getting into a lot of review of these different terms. Well, a factor is any number used in a multiplication problem. Look at 3 times 2 times 5. Each of those are factors in a multiplication problem. If I stack decimals and I multiply them, both of those are factors because they are numbers I'm multiplying together. Or fractions, both of those are factors that I'm multiplying together. However, none of those 3 examples are a base. A base is a number being used as a factor for a power. And once again, a power is any number that has an exponent, right? So I have to look at the idea of my factor is the 3 when I have 3 to the 2nd power. My base of 2 is going to be my number that I multiply together, or my factor, and I want to multiply it by itself 5 times. Or if I have 1.5 to the 7th power, I would write down 7 1.5s and multiply all of those together. So I'm taking my base and I'm going to use it as a factor, a number in a multiplication problem. And every time I would only use the base. The exponent tells me how many times to write it. So the exponent is the number that tells you how many times to multiply the base by itself. Write that down in your notes, please. The exponent is the number that tells you how many times to multiply the base by itself. So when we have powers, such as 3 to the second power, 2 to the fifth power, 1 and 5/10 to the seventh power, then I know I'm going to take the base and create math problems with them by looking at the exponent. The exponent tells me how many times to write it down in a math problem. So 3 to the second power looks like 3 times 3. 2 to the fifth power looks like 2 times 2 times 2 times 2 times 2. And 1 and 5/10 to the seventh power, yep, you guessed it, you have to write it down 7 times. And therefore you have to multiply them together. So when I multiply them together, then notice I'm not saying what is 3 times 4, because that is not the math problem. We're saying what is 3 times 3 times 3 times 3, which is not 12, just to let you know. So when I take my math and I do my different processes, then I want to be able to identify what we are coming up with. So let's look at these different terms. We have factors, exponents, bases, and powers. So the tens, what would we call those? They're factors, right? Because they're being multiplied together. What about the idea of the power? The power is the 10 to the second power, or to the power of 2. Well, what is the 10 itself then in this expression? That's the base. And therefore the 2 is the exponent, right? How many times is it being multiplied together? It's being multiplied 2 different times. Therefore, that is going to be my exponent of my power. So when I look at these, then some of these become really easy to do when I understand what the pieces are. So when I look at this expression, it says to write 7 times 7 times 7 times 7 times 7 using an exponent. Notice it's not saying to solve the answer. It's saying to write it as an expression using an exponent. So what is the base? Well, the base in this case is a 7. And how many times is it used? Well, 1, 2, 3, 4, 5 times, right? So if it's going to be 7 and it's going to be multiplied by itself 5 times, and I want to write that as an expression using an exponent, it just becomes 7 to the fifth power. That's the answer, because it's not asking you to solve it. All right, so you try the first one for the check and see how you do. Come back and check with me. So hopefully you thought, well, this is pretty easy. My base is an 8, right? And how many 8s do I have? 7, 8, 9, 10. I have 10 of them. So if I have it to the 10th power, then I have 8 to the 10th power. And that's your answer. Seems pretty easy. So what about when I have fractions? Well, don't make this complicated. Now, there's a little difference when it comes to fractions when I write them using an exponent, only because it's sometimes difficult to distinguish between my numerator being a small number and my exponent being a small number. But the same setup happens. I look at what my base is, and I count how many times it's being multiplied by itself. So notice I have 2/5 times 2/5 times 2/5. That's my base. How many times am I going to multiply it by itself? 3 times. So I know I'm going to have 2/5 to the third power. Now, once again, when I look at it though, it becomes kind of difficult to distinguish between the numerator and the exponent. So generally, when we have a fraction that we're using as an exponent in our expression, we just sit it inside of parentheses. Because notice how the 2/5 to the third power looks kind of weird, and it looks like it may be 23 over 5, which is an improper fraction, and I'm not really sure how to write it. So instead of confusing ourselves, then we learn that we just put our parentheses in around our fractions and then our exponent on the outside. And exponent on the outside of parentheses just simply means that I'm going to multiply whatever's inside by itself that many times anyway. So don't let the parentheses confuse you. It's just there really to make it clear as to what the exponent is compared to the numerator of my fraction. All right, so you using that same concept, let's figure out what 1 1/2 times 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 1 1/2 is using an exponent. Write down your answer, come back and check. So hopefully you realize your base is 1 1/2, since I said it so many times, and that your exponent is 1, 2, 3, 4, 5, 6, 7 of them, right? So if I have 7 of them, I have 1 1/2. And if there's an exponent of 7, then I just want to put my 1 1/2 inside of parentheses so that there is indeed clarity between my numerator and my exponent of 7. So hopefully you got 1 1/2 with an exponent of 7. So as we're going through the understanding of how powers work and finding products, once again, products means we're going to actually solve them. We're going to do the multiplication. They're giving us some basic information of understanding that when it comes to exponents, we do have some special terminology that we use. If we have 3 as our base and 2 as our exponent, we can say 3 to the second power. The other way of saying that is 3 squared. So hopefully you can remember that when you multiply a base times a height or a length times a width, you're finding area, you always square your label. So that's what squared means, is that you're multiplying two different things together. So if I have 3 to the second power, it's the same as 3 squared. I can also have a special one called 3 cubed, which is just simply 3 to the third power. So we will get into volume where we multiply the length times the width times the height to find the amount of space that's inside of a three-dimensional shape. But when we talk about cube, we just means that it just means it has an exponent of 3. When it comes to the fourth power, fifth power, sixth power, those don't have any special terms. So we just need to be able to understand that if it says, hey, what is 7 cubed? It's asking you what is 7 times 7 times 7. So let's go through the idea of solving these then. So this is where your handy dandy calculator should be with you because it makes your life much easier. If I see 5 to the first power, that should be pretty easy because we just have the base. We're not actually multiplying by anything. So it's just going to be 5. If it was a million to the first power, it's just going to be a million. 5 to the second power, or 5 squared, as they're showing you, gets written down as a math problem. So my factors are 5 times 5. When I do that, then I can take my handy dandy calculator. If I don't know that 5 times 5 is 25, I can check on my handy dandy calculator and I get indeed 25. 5 to the third power is how we would say that one. And I would write it down as a math problem of 5 times 5 times 5. Why? Because the exponent tells me how many times to write it down, and the base is the only thing that I will write down in the multiplication problem. Now, what I would like you to see on your handy dandy calculators is that your calculators are much more advanced than the calculators were when I was your age. If I had this math problem to do and I was allowed to use a calculator, which I wasn't, but I would have to do 5 times 5 equals times 5. Notice, and I would like you to try it, type it in on your calculator, type in 5 times 5 times 5 equals. It'll allow you to do multiple steps of multiplication, addition, subtraction, whatever, on your calculator, and then hit the equal sign. In the same way, when I have 5 to the fourth power, I write it down as the factors of 5 times 5 times 5 times 5. And when I type that into my handy dandy calculator, I don't have to hit an equal sign and then multiply by 5, and then hit an equal sign and multiply by 5. I can just type in 5 times 5 times 5 times 5 equals, and then it'll give me my final answer of 625. So when we look at the idea of 4 to the fifth power, then we want to write it down as a math problem, as an expression. So I have my product, which is going to be my answer. So I write down at my factors of 4 times 4 times 4 times 4 times 4. Once again, the base is 4. the 5, my exponent, tells me how many times to write it down. Some sixth graders will get stuck with the idea of that is just 4 times 5, which is 20, and that is never going to be the right answer when it comes to exponents and powers. So please make sure you don't get it in a hurry and try to do quick math, because this is, I need to write down my math problem, show my work, and then show what my factors are so that when I type it into my calculator and I get an answer of 1024, it makes sense. Because 4 times 5 is 20, but that's not what the math problem is. Right? The power of 4 to the 5th power is equal to 4 times 4 times 4 times 4 times 4, and that is a product of 1024. Hopefully that made sense. So I want you to try this one on your own, and I'll give you a hint. The answer is not 32. All right, so hopefully you read that and you can see that that is 8 to the 4th power. You wrote down the math problem of 8 times 8 times 8 times 8. And then when you type that into your calculator, you got 4,096. If you didn't, let's figure out why. And if you can't figure out why, please come and ask and let me help you. All right, so what about when we get into fractions? Well, please don't make it complicated. When I see that I have a fraction of 1/3 as my base, and I have an exponent of 4, notice they've written down the 1/3 as factors multiplied by itself 4 different times. And then I ask myself, can I multiply fractions? Yes. How do I do it? I multiply across. Look at your numerators. You have 1 times 1 times 1 times 1. Well, 1 times 1 times 1 times 1 is what? It's simply 1. Then when I do my denominator, I just take my handy dandy calculator and I type in 3 times 3 times 3 times 3. That's going to give me a denominator of 81. My final answer is 1 over 81, right? So when I do things such as 2/3 times 2/3 times 2/3 times 2/3, it might become a little bit more complicated because it's not just going to be 1. But don't make it complicated. Multiply across. What is 2 times 2 times 2 times 2? Well, when you type it into your handy dandy calculator, it tells you that is 16. And then my denominator of 3 times 3 times 3 times 3 is still 81. I could check and see if I could cross reduce or anything like that, and I can't. There's nothing I can reduce. So my final answer would just be 16 over 81. Does that make sense? I hope so, because I want you to do this one on your own. Come back and check your answer. So hopefully you wrote down your math problem. So I want you to do this one on your own. Come back and check, and let's see how you did. So hopefully you saw that you have 2/5 to the 3rd power, which means you wrote down your math problem to show me your work of 2/5 times 2/5 times 2/5, because I take my base and I write it however many times the exponent tells me to. And then you ask yourself, well, can I multiply fractions? Yes. Well, how do I do that? I multiply across. So in your numerators, you have 2 times 2 times 2. Hopefully, you did not get 6, because 2 times 2 is 4, times 2 is 8. And then you multiplied your denominator, and you got 5 times 5 times 5. Hopefully, you did not get 15, because 5 times 5 is 25, times 5 is 125. Well, can that be reduced? No, right? 8 will not go into 125 evenly. The only other factors are 2 and 4, neither of which will go into 125. That is as low as it can go. All right, so now it says Faith is turning 12 this year. She asked her parents to give her $2 on her birthday and to double that amount for her next birthday. If she continues with this pattern, how much money will Faith receive on her 20th birthday? So when I'm finishing up the pattern, then I can see that on her 12th birthday, she gets $2. And then on her 13th birthday, they're going to double it, right? Not give her an additional $2, but they're actually going to double it. So that's 2 times 2. And then we're going to double that again on our 14th birthday. We're going to double that again on our 15th birthday. So now after the 4 years, we have 2 times 2 times 2 times 2. But we want to go all the way to 20. So we're going to finish this chart. So on our 16th birthday, and then our 17th, and then our 18th, and our 19th, and then our 20th. So we fill in our chart, and we can see that as we go along and we increase by 2 each time. So now on our 16th birthday, we're going to multiply by 5 twos, or we would have an exponent of 5. On our 17th birthday, we're going to have an exponent of 6. On our 18th birthday, we're going to have an exponent of 7, and then of 8, and then of 9. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 twos that we multiply together. So how much money would her parents give her on her 20th birthday? Well, I don't know off the top of my head, so let's use our calculator and type it in. 2 times 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 2 equals 512. How much money will her parents give her on her 20th birthday if they start with $2 on her 12th birthday and they double it every year? They would give her $512. That's pretty good for turning 20. All right, so that is our lesson for our introduction of exponents. Once again, when we have powers, that is a math expression that is written with a base or large number and an exponent, which is the small number known as superscript. It's up above, and that tells me how many times to multiply it by itself. Exponents are important to understand because that's in our order of operations when we ask for several extra presents from my dear Aunt Sally. We must do our absolute value square roots, which we have not learned yet, but we will soon. Exponents parentheses first, followed by any multiplication and division from left to right, and then addition and subtraction from left to right. So with that being said, you now have an assignment as you're working on it. If you have questions, please come and ask. Just take your time. Don't try to rush through it. Make sure you're doing it correctly and that you are showing your work.